At this point, we've really only discussed the concept of systems of linear equations. What I want to do is bring us to the point where we're moving strictly into the material at hand, which is the concept of a vector and more generally the concept of a matrix. So let's take a look at our resource constraint problem that we discussed in the prior video, where we had the idea of these different constraints, okay? And suppose that I had a total of n variables, and that needs to, let's say, exactly equal a certain quantity on the right-hand side. And suppose I had a total of m constraints that need to hold true about those variables. Sorry, this is m1, m2. Okay, so the dot 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 means I just have like a lot of these different ones where the first one, the first index here, subscript on the variables, are representing that equation, okay? So the question then is, can I represent this in a more restricted format? And the answer, of course, is yes. One way that we restrict the notation here is by using what is called vector and matrix notation. Now, there's two ways to represent these, and I'll get into all the intricacies of this. But let's suppose that we let x with an arrow on top represent the following, and I write the following in this little bracket here, and I write x1, x2, x3, xn. Okay. Further, suppose that I say let the variable a equal the same bracket notation, but what I do is I put in a11 dot 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 a1n dot 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 am1 dot 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 amn. So I have A11, A12, A13, etc., 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 right? And suppose I do the same for B. Suppose I write B with an arrow on top, and I have B1, dot, 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 Bn. As it turns out, I can rewrite this system in a very compact way, and I can just very simply say that this is the same thing as AX is equal to B. And life is great, because what I've done is I've taken a very messy type of notation and I have simplified it down. Now, these two mathematical items are what we refer to as vectors. And this one is what's referred to as a matrix. So, put simply, a vector is a collection of numbers in specific sequence. A matrix is a generalization of a vector, where we can kind of think of it as a collection of vectors put together. Now, if we're looking at the matrix, there's two ways that we can observe a vector. We can have a vector in terms of the rows, where one row is one vector. So for example, I could have the vector A11 to A1n, right? Or we can look at vectors in terms of columns, in which case I could have, let's say, A11, A21, dot, 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 AM1. Notice how these are not the same thing, these two vectors. So vectors have this idea of being either in row format or in column format. and they're actually distinct from each other, even if the quantities are the same. All right, so for example, here's a column vector, 1, 4, 5. Here's a row vector, 1, 4, 5. As it turns out, these are not the same thing. However, we do have an operation that we can work with, which will convert the row to a column or the column to a row. For example, and I'm sorry, so that operation is what we call the transpose. We'll get much more into this as we go on. But the transpose allows us to convert a row vector to a column. Okay, so the transpose of a row vector gives us a column vector, and the transpose of a column vector gives us a row vector. So for example, the transpose of 1, 4, 5, which we usually denote like this, is equal to the row vector 1, 4, 5. And the transpose of the row vector is, of course, equal to the column vector. Okay, so transpose just flips whether or not it's a row or a column vector. If you have a matrix like the following, and you take the transpose of a matrix, what that does is switch the rows with the columns. So the first row becomes the first column, the second row becomes the second column. So all it does is just flip it. Usually, matrices are represented by capital letters, usually in bold text. Because I cannot write bold text, I'm going to be using just capital letters. So do not try to confuse these with set notation, which we also happen to use capital letters to represent. I will be clear in the context as we progress further whether or not it is a matrix or a set. However, matrices from within this lecture will predominantly be denoted by capital letters. And if you read textbooks and see bold capital letters, usually they're saying this is a matrix. So as you can see, matrices allow us to represent, as I've illustrated back here, very complex type of equations in simple form. So for example, if I have 5x1 minus 3x2 equals 4, and 2x1 plus 3x2 equals 8, I can represent this very, very easily. What I can do is say, let A be the matrix 5 minus 3, 2, and 3. Let X with an arrow. Sometimes vectors are also bold lowercase letters, but some textbooks will put an arrow over them to be very clear. Let X arrow represent x1, x2, and let B with an arrow represent 4 and 8. Then as you can see, this equation, this system of equation turns into the following: 5 minus 3, 2, 3, x1, x2 is equal to 4 and 8, which using our substitutions, we get A times B is equal to, I'm sorry, X, not B. A times X is equal to B. Now, what do I mean by times? Well, we'll get into that in a later video. But for now, I want you to get used to the idea of taking more complicated equations and organizing them into more simplistic equations using the idea of matrices and vectors. So those are the basic definitions of a matrix and a vector. a vector can be either a row or a column. And all it is just a collection of numbers, which we surround in brackets. In the vectors, each number is put into a specific location in the vector. All right, same idea here. There's a specific location in the vector. The location index can start at 0 or 1, depending on who the author is. Some will start them at 0, some will start them at 1. It's the same problem we had discussed a while back. Actually, this is n minus 1. This is actually just n. So that's the idea, okay? And for matrices, by the way, we say that A is an m by n matrix if it has m rows and it has n columns. And we usually say that Aij, the first index, almost always represents the row number. The second index represents the column number. So A12 would refer to the first row and the second column. So that would be whatever element is here. For example, in our matrix notation here, A12 refers to this number. A21 refers to that number. A22 refers to this number. And of course, A11 refers to that number. First index is row, second index is column. So those are the basics of matrices and vectors. They're just ways to organize. But as it turns out, they actually have a lot of very fascinating and interesting properties that allow us to describe not only the system of linear equations, but they also allow us to extend the theory of sets. And we'll be getting into that in some follow-up videos.